it from here on out. We're going to say that the first fundamental theorem of calculus, because this is how a lot of other people refer to it, not the person I talked to, but the majority of people refer it this way. So the first fundamental theorem of calculus is what we were working with before. Is basically a definite integral, right? You evaluate a definite integral. So that would be capital F of B minus capital F of A. And so remember, I'm using lowercase f to represent the function, capital F to represent the antiderivative. So when I talk about first fundamental theorem of calculus, that's what I mean. Second fundamental theorem of calculus last night, which says defined as g of x, and that function is the integral from a to x of t dt. Then the derivative of that function is going to be f of x times the derivative of x, which is what, sorry, yeah, times the derivative of x, which would be times 1, minus f of a times the derivative of a, which is 0. You'll notice when I do my answer keys, I typically, even though this part always goes out, I typically always show the work for that because it's me connecting back to the process. No. But I do it because it helps me remember what I'm doing better, as opposed to one is one process and one is completely different. At least they feel in my brain more related. So you'll notice I do that even though you don't have to. Which simplifies just to say that g prime of x is just f of x. Okay, so we did a bunch of examples, and we're going to add to those now. So I think this next one is example 8. I don't know if you numbered your examples or not, but feel free to do that. So for this one, we're going to do the limit as h goes to 0, and the top of the function is going to say from 2 to 2 plus h of the square root of x squared plus 1 dx, all divided by h.
This looks familiar.
Mm-hmm. It's a few things at once, like makes it really interesting. If we think about h going to 0, what's going to happen with the bottom? It's going to 0 out, right? Vertical asymptote or whatever. So we've got 0 on the bottom. If you plug 0 in for that h on the top, then you have the integral from 2 to 2, which is 0. So we have 0 over 0, which is what? L'Hopital's. Okay. Do you remember how we had to show the notation for L'Hopital's to make sure that we were getting it correct and not losing points for bad math notation? What do? We have to write it out twice. So we're going to say the limit as h goes to 0 from 2 to 2 plus h. We're going to say that equals 0. And then we're going to say the limit as h goes to 0 of h also equals 0. And we're going to say, okay, now we're using L'Hopital's. Okay, and then what do we do? Derivative of the top, derivative of the bottom. Okay, so I'm going to keep my limit notation. as h goes to 0. And then when I do the derivative of the top, this is where I'm using that second fundamental theorem of calculus, right? So what does the second fundamental theorem of calculus tell me that I should do now?
Derivative times the derivative minus the times 2.
Right. So for the first one, I'm going to take the x right here, and I'm just going to replace it with 2 plus h. So I've got square root 2 plus h squared plus 1 times, what's the derivative of 2 plus h? 1. Minus square root of 2 squared plus 1 times the derivative of 2, which is 0, so that part goes away. And then on the bottom, we just have the derivative of h. 1. Okay. So if we think about trying direct substitution again, is that going to be a problem? No, now we can just do direct substitution and we're fine. All right. So now I'm going to say square root of 2 plus 0 squared plus 1 over 1 is root 5, 1, or just root 5. All right. Here's the next example. We're going to do the limit as x approaches 2 of the integral from 2 to x of 1 over t to the third plus 1. Go ahead and make that x squared. It's from 2 to x squared, 1 over t to the third plus t divided by x minus 2. Oh, dang, we can't make that squared. Leave it as an x. Sorry, I was trying to make it have a derivative, but it wouldn't work if we don't have it go that way. All right, so when we look at the problem, remember to erase that squared if you didn't hear me a second ago. So if we try to plug in 2, what happens? The bottom zeroes out. What happens to the integral? You have 2 to 2. Anytime you have an integral that's the same number to itself, that area underneath the curve would be 0 because you have no area. So we have 0 over 0, which means L'Hopital's, which means we got to write it all out because we have to do correct notation. So limit as x goes to 2 to x of 1 over t to the third plus 1. So that limit is 0. Limit as x goes to 2 of x minus 2 is also 0. And so our conclusion is that we can use L'Hopital's. And we can't shorthand it any more than this if we want points. So, yeah, you could just say L'Hopital's. All right, so now I'm going to rewrite the limit. I've got the limit as x approaches 2, and then what should I be putting on the top?
1 over x cubed plus 1 times 1 minus 1 over 2 cubed 1 times 0.
Yeah, so all we did is we took the x and we replaced t with it. And we multiplied it by the derivative of x, which is 1. And then we took the t and we replaced the 2 for the t, and then multiplied by the derivative of 2, which is 0. And so that goes away. And then on the bottom, what's the derivative? 1. Okay. At this point, are we have a problem plugging in 2? No. So at this point, we can do our direct substitution. So I've got 1 over 2 to the third plus 1, all divided by 1, or 1/9. All right. And then one last one.
Okay, stop. Well, actually, these ones I'm doing tiny because I have some basic.
All right. What does this notation mean if we were to read it out loud?
On the integral, 0 to 8, the derivative of 1 of the square root of 1 plus x dx.
Yeah. What does it mean when it says x? If we cover this up, what would it be asking you to do?
Area under the curve.
Area under the curve or find the derivative, right? That's essentially the same thing. So take the derivative of the antiderivative. So you just get the function. Okay, so we're going to write that down. Take the derivative of the antiderivative. And if you do that, the derivative and the antiderivative cancel out, right? And you just get the function. So this is going to equal the square root of 1 plus x evaluated from 0 to 8. Have I done this notation yet? Yes, okay. In the video. I know I didn't do it in class. We just started plugging stuff in class. Okay. Okay, so we haven't done it with integrals yet. Okay, so when you are evaluating a definite integral, this is how you show what you're going to plug in. So lower bound, upper bound. All right, so we have the square root of 8 minus the square root of 1 plus 0. And so we have
2.
All right. And that's it. So we have a practice packet. I know that's shocking. One of my favorite things, I'm so glad that we tonight the notes are on U substitution, which is actually how you're going to handle being able to do integration with a chain rule problem, where it's got like an inside. So you guys have been asking me, like, can we do this? And I said, no, not yet. That's got an inside. Now we do. So we're learning about that tonight. Don't be excited. No. Hold the applause. Hold the excitement. No.
Yeah. Let's go. How much? Far it's traveled?
This is, so in a literal sense, it's saying these are the x values that you're finding your rectangles in between.
Okay.
And if you think about how to multiply out our rectangles, we're going to say the units of the x's multiplied by the units of the y's. So if this had been a rate of change, yes, it would have been like a distance traveled, because then you take your rate of change unit and your length unit and multiply them, they're going to kind of cancel out a little bit. Those units are. Like if we had multiplied by minutes, it would just be feet total. And so that's how we get that total in a sense. Yeah. In a literal sense, but it depends on the problem. Like the units and then all that stuff. Yes? So with this, it's kind of like saying these two canceled each other out. But it's the idea of inverses. Is this one's telling us to take the derivative? We know that the rest of it, the integral in this part, says take the antiderivative, and if you do a derivative and an antiderivative, they would cancel each other, and then you just get the function. I'm saying it's a definite integral, and so we have values we're going to get in the process. Yeah. Okay. Any other questions? Kind of, but I don't think that they would this technically represents width. It doesn't represent all of the antiderivative. It's the notation together that does, so I wouldn't cross them out. Does that make sense?